Okay, good afternoon, guys. So last time, I finished talking about big O and big omega, and what I'm going to do now is talk about what happens when they're both true. So we have this third notation, and you will have seen this if you've gone through the assignment, and it's called big theta notation. So if you have a function like f of x is, say, let's say 2x squared minus 3x plus 5, you could sit down and you could show that that is big O of x squared. And you could also sit down and show that that is big omega of okay, so it's big omega of x. Is there anything bigger that it's also big omega of? So is it also omega of x squared? We seem unsure, so let's prove it. I want to show that f of x is greater than or equal to c times g of x for all x at least k. Now, I didn't actually define g of x, so I'm just going to say it's x squared. So let's try to do that. 2x squared minus 3x plus 5 is definitely bigger than or equal to 2x squared minus 3x. Right? If I ignore that plus 5, I get something that's smaller because 5 is positive. So what can I do with this now? What trick do I do when I have a negative? So when you have a negative, you turn it into a positive, right? Just like in our day-to-day lives. So 2x squared is the same thing as x squared plus x squared, and I have that minus 3x, and I bracket it like this. And now that is definitely bigger than or equal to x squared, as long as x squared minus 3x is at least 0, right? As long as it's not actually a negative in disguise. All right, so I know that my c is going to be 1. And what's my k? Well, my k is anything that, the smallest thing usually, but it could be anything, such that all x bigger than that satisfy that inequality. So what we really need to do is solve this inequality. There's a couple of ways you can do it. What I suggested last time was trial and error, and there's nothing wrong with that. So let's start subbing in some values. If I sub in 1, I get 1 squared minus 3, which is minus 2. So that doesn't do it, because I want something bigger than or equal to 0. If I sub in 2, I get 2 squared minus 6, which is minus 2, which is no good. If I sub in 3, I get 3 squared minus 3 times 3 is 9, which is 0, which is bigger than or equal to 0. And we know that this thing is a parabola because it's a quadratic inequality. So I know that now that I'm at 0, I'll never dip back down because, in fact, the real sort of midpoint, or the bottom of the parabola, is higher up, right? Because I had a minus 2 here and a minus 2 there. If you don't like that, so this gives you k equals 3, by the way. If you don't like that, well, then manipulate the inequality. X squared minus 3x is exactly the same. Well, factor out the x to get x times x minus 3 is bigger than or equal to 0. When is that thing going to be equal to 0? Well, it's going to be equal to 0 when x equals 0 or when x equals 3. Right? The only way you can multiply two numbers to get 0 is if one of them is 0. And now you see, well, okay, the roots of this quadratic expression are 0 and positive 3. Therefore, taking positive 3 to be our value of k will be just fine. If you don't see that, that's okay. Just do the trial and error method. And in this course, on a test or an exam, you will always figure out the correct answer relatively quickly, assuming you split it up well. right? And if you split it up in a really weird way, then I can't control how you do it, right? You could split this up, say if it was x squared, you could split it up into 1 over 1000x and 999 over 1000x. Okay, I don't know that that's the obvious way to split it up. I would usually go half and half. Okay, in any event, our answer here is k equals 3. So c equals 1 and k equals 3 show that this function, 2x squared minus 3x plus 5, really is omega of x squared. And we already know that it's big O of x squared. I'm not going to do that, but we should all know how to do that by now. So in this situation, f is bounded above by x squared, and it's also bounded below by x squared. So we say that fx is theta of x squared. So maybe I'll write out the full function. The full function is 2x squared minus 3x plus 5. 2x squared minus 3x plus 5 is theta of x squared because it's bounded above and below. So theta you get for free by doing the other two, right? Just like when you were trying to prove that a function was bijective, you proved that it was injective and surjective. Well, to prove that a function is theta of another, you prove it's O and omega of the other. Same kind of thing. So when I ask you to do a proof that some function is theta of another function, I'm really asking you to do two proofs. One that it's big O, one that it's big omega. So fx is theta of g of x if and only if fx is big O of gx and fx is omega of g of x. They both have to be true. Does that make sense? So if you want to think of it in a different way, and this is helpful to some people, if you don't find it helpful, don't think of it this way. Less than or equal is to numbers as big O is to functions. Right? Less than or equal gives you an upper bound on a number. Greater than or equal is to numbers as big omega is to functions. And equal is to numbers as theta is to functions. All right, that's one way you can remember what's going on. And the nice thing about this is that the less than or equal that goes with big O, well, that's the direction of the inequality you have to prove, and vice versa for omega. One word of caution, when I ask you to do a proof of theta, you will get two different C's and two different K's. I suggest calling them C1 and C2 and K1 and K2. So the constant you get in your big O proof does not have to be the same as the constant you get in your big omega proof. And similarly for the K's. So they can be the same, but they don't have to be the same. So if you're doing these, make sure you give them different labels, because if your variable names conflict, just like a compiler would get confused, so too will your TAs and will me if you do something like that. So any questions about big theta? I'm not going to do a ton of examples of theta because that's really just a bunch of examples of O and omega, and I've already done that for you. This is okay? All right, so we're ready to revisit something we talked about earlier in the course, and that is proof techniques. We're now ready to learn another proof technique, and that technique is called induction. So this is an important proof technique that will come up a lot in theory courses in CS and in math courses in general. So it's important to really understand this. This comes up again and again throughout your degree. And the way induction works is, well, if you think back to when we made the jump from proposition logic to predicate logic, we said that the universal quantifier was essentially shorthand for a big conjunction. but I didn't tell you really how to prove that a universal quantifier is correct. And I didn't really show you how to do that in general, and the reason is it's kind of hard. So we know this one trick, this universal generalization trick, but that seems difficult to apply because we have to deal with this arbitrary element, and we don't really have a lot of leverage on it, right? We don't know anything about it. So what induction does is it lets us do this kind of universal generalization proof, but it gives us a little bit more leverage so that we know something when we're doing that. Now, if that seems weird, let me define what it is and give you examples, and hopefully it'll be clear. So I'd like to pose a question, and the question is, what is the sum of the first n positive odd integers? So we've already seen what it is if it's just the first n positive integers, right? It's n times n plus 1 over 2. We've already seen that. I'm asking about the first n positive odd integers. And notice in this proof, or in this question, I'm not giving you any hint as to what it should be. It isn't prove this formula is correct. I'm just posing the question. So if you were encountering this, or if I were encountering this, the first thing I would do is start plugging in values. Always being mindful of the fact that a bunch of examples is not a proof, but doing a bunch of examples can help you figure out what the answer is, and later you can prove that. So let's do that. If I want to know the sum of the first one positive integer, well, that's just 1, and that sum equals 1. So that's not too interesting. What about the sum of the first two positive integers? Well, the first two positive odd integers. The first two positive odd integers are 1 and 3. And if I add them together, I get 4. All right. What about the first three positive odd integers? Well, that's 1 plus 3 plus 5. 5 and 3 is 8, plus 1 is 9, so I get 9. The first four positive odd integers are 1, 3, 5, 7. 7 and 5 is 12, plus 3 is 15, plus 1 is 16. Does anyone have any guesses as to what's happening? Yep. Yeah, it looks like it's going to be n squared, right? 1 is the same as 1 squared. 4 is the same as 2 squared. 9 is the same as 3 squared. 16 is the same as 4 squared. And in all of these cases, I get n squared. So it seems like that's the answer, but I only have 4 pieces of evidence to back me up, and there's infinitely many values of n. So I have a very tiny fraction of evidence. So it looks reasonable, but I'd like to prove that it's true. And the thing that makes this hard, the thing that makes this different from what we've seen before, is the fact that n can be any integer. Right? N can be any positive integer, we'll say. So how do you prove something is true for every single integer? There's infinitely many of them. We've already seen that. There's countably infinitely many of them. So it seems really hard to do that. Right? We need to prove something's true, and if we, for example, wanted to do a proof by cases, we'd have infinitely many cases, and that would be difficult. All right, so let's take a step back for a second and think about how we could do this. So imagine a long line of people. And let's say the people are numbered 1, 2, 3, and so on. So there's this really long line of people. I don't know how long. And suppose that whenever person K is told something, then person K tells person K plus 1. Okay, and that's true for any K. And my question is, What happens if I tell a secret to person 1? What's going to happen? Yep. Everyone in the entire line will know the secret. Does it matter if there's infinitely many people in the line? No. I mean, it might take a while, but everyone will know the secret. All right? So if you don't believe that, we can prove it. We know how to prove it. Let Pn denote the proposition person n knows the secret. Well, we're trying to prove something, and a proof is really just an argument. So really, what we have is a premise, and that is that whenever person k is told something, they tell person k plus 1. So for all k, if pk knows, then pk plus 1 knows. Right? That's our premise. And the other premise is that I told person 1. So person 1 knows the secret. So P1 is true. And the conclusion that I'd like to draw is that everyone knows the secret, because that's what we said the answer was. So that means for all n, Pn. So originally I only know one thing. I know that person 1 knows the secret, but I also have this fact that says whenever someone knows the secret, they tell the next person. So I'd like to prove that this thing is true. So one way I can see that is by applying our usual rules of inference. So first I'm going to do universal instantiation on 1. And I'm going to instantiate with k equals 1. So I know that P1 implies P2. And that's by ui of 1. And I know that P1 is true. Therefore, P2 has to be true. And that's by modus ponens of 2 and 3. So now P2 is true. So what I do then is I do ui again, except this time I instantiate with k equals 2 to give me P2 implies P3. That's ui of 1. Same trick again. Well, now I know P2, and P2 implies P3. So therefore I know that P3 is true, and that's by modus ponens of 4 and 5. And this pattern keeps on going, right? That's going to keep on going. I can drive P2, I can drive P3, I'll be able to drive P4, P5, P6, P7. And this pattern just keeps on going, right? Nothing's going to interfere with what's going on here. So eventually, at step infinity, if you like, I will have P1 and P2 and P3 and P4 and so on. And that's just by conjunction of, a bunch of stuff. And now I have the conjunction that says the predicate P is true of everything in the universe of discourse. And that's exactly the definition of the universal quantifier. So this thing here is exactly the same as for all n Pn, which is my conclusion. So what I did here was I took a statement that seemed really difficult to prove, a statement about infinitely many people, or infinitely many positive integers, if you like, and I showed it was true, and the thing that let me prove that it was true was this thing here, this premise 1, the fact that I knew that whenever pk was true, so was pk plus 1. That's what let me do it, because that's what allowed me to apply modus ponens. Okay, so this last step here is by definition of for all. So this actually gives us a proof technique when the universe of discourse is the natural numbers. Yeah?
Other than the equation of 0, 1, 1,
Right, so this is a little bit different because I've established a clear pattern. So if I sat down here and wrote out all the way to P1000, I would definitely be able to do it. The reason I don't is because it would take a long time. Yeah, that's different from doing a couple of examples and assuming the pattern will continue. Because in that case, you don't know what the pattern is. You know what the pattern appears to be. In this case, I know what the pattern is. Yeah.
And how do you know what the pattern is?
Because I could do this in general, right? I could say, okay, well, the next one is P4. Let me just do this down here. 7 would be P4 implies P5, and that's by UI of 1. And then the next one would be P5 by modus ponens of, oh, I skipped one. That should be 3 and 4. Modus ponens of 6 and 7. So what's always happening is I get something like, so let's call this step X. I'll get P something, so let's say, I don't know, P something implies P something plus 1. And then in step X plus 1, I will get P something plus 1. So this one was by UI of 1, and this one will be modus ponens of X minus 1 and X. That's how I do that. And you can fill in the blanks with whatever's appropriate, like X over 2 or something like that. So that's why this pattern works. That's what it looks like in general. Other questions? Yeah?
And the other one didn't work this way? You didn't do a proof like that?
Right. Well, you wouldn't know what pattern to write down, right? You know what the pattern, you know what you think the pattern is, but you don't have a pattern to write down there. Yeah?
This one's just kind of circular, but like, even though we can write down a pattern, haven't we still not proved that it's correct?
We have. It's just that the pattern is too long to write out. So just like we all believe that the universal quantifier works, I never actually wrote out what the universal quantifier was in full, because it's shorthand for something that's infinitely long. Other questions? All right, so this gives us a proof technique. And specifically, it gives us a proof technique to prove for all x, px, when the universe of discourse is the natural numbers. So either starting at 0 or 1, in fact, it doesn't matter. And we'll see a little bit later on that it works for an even broader set of universes of discourse. So basically, to summarize what this means is we have P1 and for all k, pk implies pk plus 1, 2, 3, 4 implies for all npn. So if we can show the thing on the left, then the thing on the right is true as well. Okay, that's all we have to do. So it seems like this is way worse, right? This is much more complicated than any of the proof techniques we saw before. Do you understand where this implication came from, by the way? So I have an argument, so I want all of my premises to imply the conclusion. My premises were P1, and for all k, pk implies pk plus 1. So I take the conjunction, and they have to imply the conclusion. Yeah?
And that's only possible because there's a starting point within your set of universal discourse?
Yes. This is a related idea, but that is important. So you couldn't do something like this for, say, the set of real numbers. That wouldn't work because there's no smallest real number. You can do something kind of similar if you include negative numbers, but then you have a different starting point that's the first thing you want to prove that it's truthful. Other questions? Yeah?
You start at 0 and then go up and then do another proof going backwards?
To prove something was true for all integers positive and negative?
Yeah.
Yeah, there are techniques to do things like that as well. You have to be a little bit more careful about some of the steps I'll talk about, but there are ways of proving stuff is true for all integers. Yeah. Other questions? All right, so this seems like it's worse, so why do we care? So why do we need, and therefore like, this? Well, the idea is, before we did any of this, so earlier in the course, before we knew how to prove for all x, ax implies bx. Right? We already knew how to do that. The way we did it was to pick an arbitrary x and do a direct proof. Right? This is the universal generalization trick. Pick arbitrary x and do a direct proof. So that's the trick we used to do for things like this. But the problem is that this doesn't always work. Now, I didn't give you any examples where it didn't work, because that would be kind of mean. But it doesn't always work easily. What we've done is we've converted the proof of for all n Pn into an implication. So I want to prove for all n Pn, but instead I'm going to prove this thing, and that's usually pretty easy because it's not quantified in any way. And then I'm going to prove this thing, and that seems like it's worse, but it's actually easier because it's easier to prove an implication. We like to prove implications because if we're going to prove an implication, we usually do a direct proof of that implication, right? That's the first thing we said we'd try. And when you do a direct proof, you get to assume that the thing on the left is true. And whenever you get to assume that something is true, you should be happy because that gives you leverage into doing the proof. The more facts you know, the more able you are to do the proof. So by assuming something, by going to this implication, we get more leverage, and that's what we're looking for in the proof. So therefore, we can use a direct proof, and a direct proof gives us the ability to assume something. So the thing we assume is on the left. And this assuming something, that gives us more leverage into proving that whatever we're trying to prove is true. So this is all kind of high level and abstract. Once we start doing some examples, you'll get a better feeling for this. Before we do that, though, I just want to name a few of these things. So this P1 here, that's called the basis step. So if I want to prove that this implication is true, I need to prove that both of these things are true. All right, so first I have to prove that P1 is true, and doing that is called the basis step. And then this other thing here, PK implies PK plus 1, this is called the inductive step. And in particular, this PK, this is called the inductive hypothesis. Right? Because I'm going to prove the implication for all k, pk implies pk plus 1. So what will end up happening is I'll take an arbitrary k, and because that's what I have to do for universal generalization. And I'll assume the thing on the left, which is pk. So that's why I call that my inductive hypothesis. All right. So let me talk about these terms a little bit first. So P1 is the basis step. You might also hear this referred to as the base case. That's the same thing, and I'll probably call them both. I call it both. PK implies PK plus 1 is the inductive step. So we're trying to prove P1 in our base step, in our basis step, and we're trying to prove PK implies PK plus 1 in our inductive step for an arbitrary K. So we are doing this for an arbitrary K, just like in universal generalization. So typically, we do a direct proof. That's what we'll do in basically all of the examples we'll see. And so we call PK the inductive hypothesis. All right, and we assume that it's true in order to prove PK plus 1. So we assume that PK is true in order to prove PK plus 1. That's the idea. So one thing I need to stress here is that we're not assuming that PK is true for all positive integers. That's not what we're doing. We're assuming that PK is true for some arbitrary integer, but we don't know what it is. So that's different from assuming it's true for all positive integers. Because if I assume that PK is true for all positive integers, that would be circular reasoning. Right? I want to prove that for all n Pn, and if I assume that for all k pk, well, it doesn't matter what the variable is, that's circular logic because I'm assuming what I'm trying to prove. I can't do that. So we are not assuming that pk is true for all k. We are not doing that. We're only assuming it's true for some arbitrary k. Oops. At some point in the future, possibly in April, you'll be asked what you are assuming when you make an inductive hypothesis. The answer is that it's true for an arbitrary k, not for all k. Lots of people made this mistake in, say, December of last year. Okay, so now that we have these definitions, let's go back to the question I posed earlier about the sum of the first n positive odd integers, and let's show that our guess of n squared is in fact correct. All right, so when you're doing a proof using this induction technique, which is called proof by induction, what you need to do is label each part of the proof, say what you're assuming, and say what you would like to prove. The TAs will give you part marks for following the correct format of a proof by induction. So you will get marks just for saying what it is you want to prove even if you're not able to prove it. Okay, so it's important to understand the format of what's going on. I'm going to do a ton of these examples. Make sure that your proofs are formatted like my examples. They don't have to be exactly the same, but all that I have here needs to be in your proofs. So, the first thing you should always do is the basis step. So you write down basis step in a clear way so that the TA knows where your basis step is. If you make the TAs look for where your work is, they will be upset and less willing to find you marks. All right. So now we think to ourselves, what does our universe of discourse look like? Right? We need some starting point. So when we were doing the people example, I said I told person 1. Well, everything I said would have gone through just fine if I had told, say, person 5. But the result would have been different. It would be every person 5 and later know the secret, but people 1, 2, 3, and 4 might not. So you can apply proof by induction to other settings. Just be mindful of what value you're doing in your basis step. Now for us, we're asking for the sum of a bunch of integers, and it really only makes sense if you start that at 1. You can have a sum with 0 terms, and it's 0, and 0 squared does happen to equal 0. But we're going to ignore that for now. So in the basis step, you show P of whatever the smallest thing you want to apply your statement to. For us, it's 1. The smallest n is 1, so our basis step is at 1. All right. So before we do this, I'll let Pn denote the sum of the first n positive odd integers is n squared. So in the basis step, I want to show P1. So I say we must show P1. So now you show that P1 is true. P1 says that the sum of the first 1 positive odd integers is 1 squared. And 1 squared is the same as 1. So 1 equals 1, which shows that the basis step is true. Does everyone see that? The sum of the first 1 positive odd integers is, well, the first positive odd integer is 1. And if you sum up one number, you get whatever that number was, and it's equal to 1 squared. So P1 is true. It's correct. So now we move on to doing the inductive step. But before I do that, you should write down the inductive hypothesis. So inductive hypothesis. You write down what it is you're going to assume. So let's go back up here. The inductive hypothesis is pk for an arbitrary k. So assume that pk is true for an arbitrary k. Arbitrary is important. So what that means that 1 plus 3 plus 5 plus something, what is the kth positive integer? Positive odd integer, sorry. Yeah, 2k minus 1. Why isn't it 2k plus 1? So, I mean, the short answer is that's 1 too many. But if you don't see that, well, what's the sum of the first one? Well, if it was the first one, k would be 1. and I have 2 times 1 minus 1, which is 1, and that's the correct answer. So that's how I know that it's 2k minus 1. And if pk is true, then this thing equals k squared. Right? If pk really is true, then what pk says is that that summation is correct. You're allowed to assume it because you're trying to do a direct proof of an implication. And when you do a direct proof of an implication, you assume the thing on the left is true, and you show the thing on the right is true. All right, so now that we have that, we do our actual inductive step now. So we, again, label that. So inductive step. And the first thing you should do in your inductive step is write down what it is you're trying to prove in your inductive step. Because if everything goes wrong in the inductive step, you can still get some marks as long as you say what you were supposed to show in your inductive step. That's really, really important. So we want to show that pk plus 1 is true. And we do that using the inductive hypothesis. So pk plus 1 says that the sum of the first k plus 1 positive odd integers is k plus 1 squared. Remember your brackets. All right, so what you cannot do is write this out, but with a 2k plus 1 equals k plus 1 squared. You can't do that because that's what you're trying to prove. I want to prove something about 1 plus 3 plus 5 plus all the way up to 2k plus 1. And now it's 2k plus 1 because I'm looking at the sum of the first k plus 1 positive integers. So I want to know something about this sum. I can't just say it's equal to k plus 1 squared because that's what I'm trying to show. I'm trying to prove that this is equal to k plus 1 squared. So that means I'm trying to prove that one thing is equal to another thing. So what I do is I start on one side and I write down a bunch of steps until I get to the other side. Right? That's how we prove that two things are equal. All right, so I have this sum, and I don't know anything about it, but I do know something about this other sum, 1 plus 3 plus 5, all the way up to 2k minus 1. So what I'd like to do is somehow change what I have here to have something I know about inside of it. So this sum here is exactly the same as 1 plus 3 plus 5, all the way up to plus 2k minus 1 plus 2k plus 1. Does everyone agree that that's exactly the same? I'm just writing down the last two terms instead of including it in the dot, dot, dot. So now that I have this, well, I look and I say, well, this thing here, I know something about that. My inductive hypothesis said that it was exactly equal to k squared. So this thing here is exactly equal to k squared, and that's by the inductive hypothesis, which usually gets abbreviated IH. So that means I can actually write k squared plus 2k plus 1. So that's kind of nice. Now I don't have these ellipses anywhere. What's k squared plus 2k plus 1 equal to? Yeah, that's k plus 1 squared. If you factor that, you get k plus 1 squared. If you don't believe me, k plus 1 times k plus 1. K times k is k squared. K times 1 is k. 1 times k is k. 1 times 1 is 1. So that's k squared plus 2k plus 1. So that's good. What have we shown? We've shown that this thing up here, which is the sum of the first k plus 1 positive odd integers is exactly equal to k plus 1 squared. And therefore, pk plus 1 has to be true. Because I showed that what pk plus 1 says is in fact true. That sum is exactly equal to k plus 1 squared. Is this okay? So this is actually the entire proof. I'm now finished, so I would maybe say, since the inductive step is true and the basis step is true, therefore it must be the case that for all npn. Okay? And that's exactly what we wanted to prove. So now we do have a proof that the sum of the first n positive odd integers is exactly equal to n squared. Any questions about doing this proof? Yeah?
Can you say what you said again before the inductive step is true?
Right, so if you look back to the proof technique, our proof technique is this thing here, and it's to prove that this implication is true. And one way to prove that this implication is true is to prove this thing here and that thing there. Because whenever both of these are true, for all npn is true. So because it's a conjunction, I need them both to be true. So I need to prove that p1 is true and the big thing is also true. So the statement is, so remember this is a proof, so it's really just an argument. And an argument is true if the truth of the premises implies the truth of the conclusion. So I only care about the case when the premises are true. So I mean, another way to view that is if the thing on the left is true, then the thing on the right is true. It doesn't say anything about the case when the thing on the left is not true. Other questions? All right, so now that we've seen an inductive proof, I want to do a few little notes about it. So a few notes about proof by induction. So you absolutely have to remember the structure. That is critically important. If you're not able to do the proof, you will lose marks, because that's the question. But if you at least remember the structure, you will still get quite a few marks. So that's important to be able to do. The structure is the following. It's the basis step, the inductive hypothesis, and the inductive step. That's the structure. And you should label them. That's important. And in the inductive step, you should always state what you're trying to prove. So the TAs, in this course, our goal is to make sure that you know how to do induction. Our goal is not to make sure that you know that the sum of the first n positive odd integers is n squared. That's not what we're trying to teach you in this course. We're trying to teach you induction. So if you can demonstrate to the TAs that you know what induction is, even if you can't complete a question about induction, you will still get marks. And the exam is designed to reward that knowledge, even if you have trouble doing it in particular specific cases. So do you need to know how to do it to get full marks and succeed in doing it? Yes, of course. But it's a good idea to at least know how to do it, even if you can't apply it to every single case you come across. So don't leave those questions blank. Please don't leave proofs by induction blank. At least do the skeleton of what it is you need to prove. All right. And then the last point I'll make here, and this is a common source of confusion, you don't have to define those propositional functions. So of course it is necessary to define them if you use them. I'm saying you don't have to use them. So remember, don't use one unless you explicitly define it. So if you look back at the last proof we did, you might say, well, using p didn't really help you anywhere. You could have just written it out every time. And you're right, and that's what we'll do from now on. I just wanted to do that so you could see how it related to the original sort of induction. In general, that's more work than you need to do. That extra notation doesn't really get you anything. Any questions about these notes? Yeah. Especially. Explicitly define it. Yeah, explicitly define it. Okay, so are we ready for more examples of induction? Yeah. Yes, so the inductive hypothesis is what you're trying to prove, but at a smaller value, basically. You don't know what that value is because it's arbitrary. You don't get to choose it. But in the example above, pk was that so the sum of the first k positive odd integers was k squared. Pk plus 1 is the sum of the first k plus 1 positive integers is k plus 1 squared. So you assume that it's true for some smaller value than your arbitrary value, and then you prove that it's true for the next one. That's really what it is. So it's just like in that example of telling secrets. I assume that if one person knows, then the next person knows. I don't know which person that is, but I still make that assumption. Does that answer your question? Yeah. Other questions? All right. So induction works on inequalities too. Let's prove that n is less than 2 to the n for all positive integers n. So we have these three parts as usual. We have a basis step. So in our basis step, we need to prove that it's true for the smallest value of n to which the claim applies. So what's the smallest value of n to which the claim applies? Yeah, n equals 1. Right? The claim is that that inequality is true for all positive integers n. So what's the smallest positive integer? It's 1. Right? It's not 0 because 0 is neither positive nor negative. And in fact, is this wrong if n was 0? So if n was 0, the left side would be 0, the right side would be 1. So in fact, it's still true, but that doesn't matter. The claim is true for all positive integers n, so you need to prove that it's true for all positive integers n. Now, in fact, if you went one too small, that's okay. But if you went one too big, you would lose marks. So if I did this proof starting at n equals 2 for some reason, I would lose marks because I only proved that it was true for all positive integers at least 2. And that's not what I wanted to do. So in the basis step, I have n equals 1. So I must show that 1 is less than 2 to the 1. Well, 1 is 1, and 2 to the 1 is 2, and that's true. So I'm happy. The basis step is typically fairly easy, right? That doesn't mean you can forget it, because if you forget it, it could be that the claim is incorrect. Okay, so next comes the inductive hypothesis. In the inductive hypothesis, I want to assume that k is less than 2 to the k for some positive integer k. What you definitely cannot write is assume that k is less than 2 to the k for all positive integers k, because that's exactly the same as for all k is less than 2 to the k, which is exactly the same as for all n is less than 2 to the n. So it's for some positive integer k. It is not for all positive integers k. I promise that someone will get that wrong. Don't let it be you. All right, so after the inductive hypothesis, we have the inductive step. In the inductive step, you should always start by writing down what it is you have to show. So we must show what? Yeah. You assume the inductive hypothesis is true. So I know that k is less than 2 to the k. Yeah? I want to show that k plus 1 is less than 2 to the k plus 1. And you always need to be careful subbing in the k plus 1 for k. Watch brackets and exponents and things like that. Those are easy to forget, and then you'll be off. All right, so I want to show that this inequality is true, and I know that k is less than 2 to the k. So to prove that an inequality is true, you start at one side of it. So in our case, I'll take the left side, and you work your way to the other side, so to the right side. So what's one thing that's definitely bigger than k plus 1? Well, I know that k is less than 2 to the k, so k plus 1 is less than 2 to the k plus 1. And I know that because k is less than 2 to the k. And that's by the inductive hypothesis. Everyone sees that? So you need to be comfortable with working with inequalities. There's no way around that. All right, what's one thing definitely bigger than 2 to the k plus 1? 2 to the k plus k is bigger, but I'm going to go even bigger than that. I'm going to say 2 to the k plus 2 to the k. And I know that because 1 is less than 2 to the k. How do I know that that's true? Right, I can assume that k is greater than 1. Right? This wouldn't be true if k was smaller than 1. Right? That would be a problem. So I know that, because I know I'm proving it for all positive integers, I know that that's true. So this is since k is at least 1. Question?
Yeah, is it k plus 1 is less than 2k plus 1 or 2 to the k plus 1?
2 to the k plus 1. So the plus 1 here is not in the exponent. If it were, we'd be done, right? Because that's what we're shooting towards. Okay, so now I have a 2 to the k plus 2 to the k. What's this exactly the same as? So let's say I had a plus a. What would that be the same as? 2a. So this is the same as 2 times 2 to the k. And what's 2 times 2 to the k the same as? 2 to the k plus 1, because I know my exponent laws. So again, you'll need to know your exponent laws. So what did I do? I showed that k plus 1 is less than 2 to the k plus 1. And if I look back at the first line in my inductive step that showed me exactly what it is that I was trying to do, that is in fact exactly what I was trying to do. So that's why we write down what it is we're trying to prove. We write it down so that we know when we're done. And in this case, I know I'm done because I got to exactly what I wanted to prove. So without wanting to belabor that too much, this thing here is this. This thing here is this. So that's how you prove an inequality is true. You start at one side, you work your way to the other side. What you absolutely cannot do is assume that this is true. So if you write down k plus 1 is less than 2 to the k plus 1, and then start doing things to that inequality, that's not a proof. Right? It's not a proof because you're assuming what it is you're trying to prove. The only way that will work as a proof technique is if all of your manipulations are if and only if. Because then you could read it bottom to top and it would still be correct. I caution you against doing that. When you're doing an inequality or an equality, you almost always want to start on one side and work to the other. Does that make sense? Yeah. No, you can make a case for starting at both. Typically, you want to start on the side that's simpler, but not necessarily. It really is possible to do these things different ways. I like to start on the simpler side, which in my mind is the side with just a k instead of 2 to the k. But even then, there's not really a rigorous definition of what simpler means. So you get a feel for it as you get more experience. Yeah?
Just what we were just doing, you just proved the inductive step is true.
Yes. Yeah, that shows the inductive step is true. Other questions? All right. Yeah, no, now we're done. So once you're finished, so you need to do the basis step, the inductive hypothesis, and the inductive step, and you're done. That's all you have to do. Other questions? All right. So let's do some more notes. Now that we have a bit more experience. So some other notes. Not to belabor this too much, but always write out what you must do. And that usually comes up in the basis step and the inductive step. So always, always write it down. It helps you, it helps the TAs, it helps everyone. Just write it down. In the inductive step, you have to prove that pk plus 1 is true. So you can't assume it. Right? If I ask you to prove that something is true, we can all agree that you can't just assume that it's true and use that fact in your proof. That's not a valid proof technique, and yet this happening is somewhat inevitable. Yeah? So you could do a proof by contradiction here. That becomes somewhat delicate, but there are ways of doing proofs by contradiction here. Yeah? Other questions? All right, so you can't assume pk plus 1. Notice in the last proof, I started with one side and derived the other. I didn't just take pk plus 1 and mess around with it to get to pk. The last sort of point is that, well, how do you know when to use mathematical induction? So whenever I introduced a new proof technique earlier on in the course, I always said when it is that you should use it. The hint that you should use mathematical induction is statements like, for all positive integers. That's the most common one. If you see something and you're being asked to prove that it's true for all positive integers, that's a hint that you might want to consider using induction. So look for statements like for all positive integers, or sometimes it's for all positive integers bigger than 5 or something like that. But the key thing is that it's for infinitely many integers. That's really the hint. Okay? And it's not just that, but it's in general other signs of universal quantification. Right? That's the hint. And what's more, it's not just any universal quantification. It's universal quantification where if you tried just to pick an arbitrary element and do the proof, you probably wouldn't get anywhere. So if you tried to do it the way we've already seen, where you pick an arbitrary element and just try to prove it like that, and you sit down, you try really hard, you can't do it, then that's a hint that you might want to try induction. So especially if picking an arbitrary element and attempting UG doesn't seem to work. Questions about that? All right, so let's see another example. Induction can be used to show things other than just equalities and inequalities. So the next example I'm going to do is with divisibility. So I want to prove that n cubed minus n is divisible by 3 for all positive integers n. So what I mean by divisible, if you did the division, there wouldn't be a remainder. So if you divided n cubed minus n by 3, you would get some integer with no remainder. Is that clear? All right. So we'll do a proof. Start with a basis step. In the basis step, I do the smallest value of n to which the claim applies. The claim is n is a positive integer. The smallest positive integer is 1. So I do n equals 1. All right, so we must show that 1 cubed minus 1 is divisible by 3. So 1 cubed minus 1, that's equal to what? 0. And is 0 divisible by 3? Well, 0 divided by 3 is 0, remainder 0. So yes, right, it is divisible. Okay, so the basis step is true. Now I do the inductive hypothesis. I'm just going to abbreviate that. Inductive hypothesis, well, I assume that k cubed minus k is divisible by 3. And that's for some positive integer k. I always get asked the question, why you switch from n's to k's? I do that to remind myself of the fact that k is arbitrary. And it's completely different from this idea of n in the statement of the thing to be proved. So that's why I always switch to k. Other people use I. That's fine too. But I like to use a different variable so that it's clear to me and to everyone that it's some arbitrary thing that I have no control over. All right, so that's my inductive hypothesis. In my inductive step, I want to show that what? That k plus 1 cubed minus k plus 1 is divisible. Divisible by 3. Here's a common mistake, is forgetting those second parentheses. Right? If you forget these parentheses here, you will do this incorrectly. because this is equal to k plus 1 cubed minus k minus 1. And if you leave off the parentheses, you'll have minus k plus 1. And those differ by 2, so if one is divisible by 3, the other one definitely isn't. So that's something good to keep in mind. You could write it directly like that. I prefer to do it this way just so it's clear what you're plugging in to this statement. All right, so I want to show that this thing is divisible by 3, and I know that k cubed minus k is divisible by 3. So what I do is I start working with this thing until something happens and I get a k cubed minus k. I know that part's divisible by 3, and then hopefully everything else will work out. That's my hope. So, k plus 1 cubed minus k plus 1. What's that equal to? Well, let's start with the k plus 1 cubed. What's that the same as if you expand it out? Yeah.
K plus 1, oh, sorry, no, I'm thinking this is k plus 1 bracket, bigger bracket, k plus 1 squared.
Right, so you could factor that out, factor out a k plus 1. That's okay, but the way we're doing our simplification is we want to somehow get a k cubed minus k. That's what we're shooting towards, because that lets us apply our inductive hypothesis. So rather than factoring a k plus 1 out, it's going to be easier, even though it's more work, to expand this thing out so I get the k's on their own away from the k plus 1s. Yeah? Exactly. So how did you do that? Okay, so Wolfram alpha. Okay, yeah, so there is a way of doing this. Pascal's triangle, as you alluded to. So really, it's just Newton's binomial theorem. We used to teach that in this course. So if you can imagine, we jam-packed even more into this course than there already is. But now that's in 2804. If you don't know how to do this, that's okay. You can just do it out the long way. So k plus 1 cubed, well, that's the same thing as k plus 1 times k plus 1 squared. K plus 1 squared is k squared plus 2k plus 1, and then you expand it out with k plus 1, and you'll get exactly this. It's a bit of work, but that's how you do it. And I still have this minus k plus 1 here. So now I manipulate this a little bit. Let's get rid of all the brackets. So minus k minus 1. So the plus 1 and the minus 1 cancel. And I'm going to bring the minus k over. So k cubed minus k plus 3k squared plus 3k is what I'm left with. And I'm going to simplify this a little bit more. I'm going to factor out a 3 from the other side. And my claim is that this number is divisible by 3. Why is this number divisible by 3? Yeah, I know that the thing on the left is divisible by 3. Yeah, so this thing is just divisible by 3 by the inductive hypothesis. This thing here is divisible by 3 because it has 3 as a factor. So if I told you, hey, here's a number of 3 times x, is that going to be divisible by 3? The answer is yes, because you divide it by 3, you get back x, assuming x is an integer. Okay. So if you divide this number here by 3, you get k squared plus k. Since k is an integer, k squared plus k is also an integer. And this also relies on the fact that when you add two things that are divisible by 3 together, you get something that's divisible by 3. Why is that true? Yeah, you have a factor of 3 in both terms. So what you could do is factor the 3 out to the outside, and then the whole thing has to be divisible by 3. All right, so because both of those are divisible by 3, the whole thing is divisible by 3 because both terms are. And that's exactly what I wanted to show, right? I wanted to show that k plus 1 cubed minus k plus 1 is divisible by 3. This thing here is k plus 1 cubed minus k plus 1, and I showed that it is in fact divisible by 3. Yeah?
K cubed minus K is only divisible by 3 because
You mean the inductive hypothesis? Yeah.
yeah. I'm just a little bit confused about this. Can you show the way we represent it in the argument?
Yep, so I would have, I'll do this off to the side here. The first premise would be the basis step. So that is 1 cubed minus 1 is divisible by 3. And the second argument would be for all k, if k cubed minus k is div by 3, then k plus 1 cubed minus k plus 1 is divisible by 3. So this is a little bit harder because I don't have these propositional functions anymore. If I defined it as Pn is n cubed minus n is divisible by 3, then I would have the same format that I did earlier. So really the same thing is happening. I'm saying, okay, well, 1 cubed minus 1 is divisible by 3. And in general, if k cubed minus k is divisible by 3, then k plus 1 cubed minus k plus 1 is divisible by 3.
Oh, and then for every K.
Yeah, it's a little bit like a domino effect kind of thing, right? So the dominoes are all lined up next to each other. The fact that they're all 1 unit away from each other, that's essentially the inductive step. And then you flicking over the first one, that's proving that the basis step is true. That's really what's happening. Other questions? Okay, so before we go, I just want to make one more remark, and this will lead into the examples we do next time. There's nothing special about starting at 1, and this is something I've already alluded to. So you can start anywhere you like. So at any integer, let's say b, and you do this by using b in your basis step. And doing this proves the statement over the universe of discourse b plus 1, b plus 2, and so on. So if you start at 5, that will prove that it's true for all integers at least 5. It doesn't say anything about 0, 1, 2, 3, and 4. All right, so that's it for today. Next time we'll see a bunch more examples of proof by induction.
What is special about